Okay, here's the second part of these videos on deriving these formal trig identities. In this one, we'll pick up where we left off, which was we had these identities for cosine's difference, cosine alpha, cosine beta plus sine alpha, sine beta, and cosine's sum, which we saw maybe they're going to be kind of useful. Sine alpha, sine beta. And what we'd like to now is come up with some similar formulas for sine and for tangent. So first, sine. This is still going to be a lot easier than that very first one that we ever worked out. Let's say I'd like to know about sine of alpha plus beta. What I can do is I can say right off the bat that I know that sine of alpha plus beta is equal to cosine of pi over 2 minus alpha plus beta. So I'm using my cofunction identity, just using radians there instead of degrees. Now what I'll do is I'll distribute that minus sign. So I'll have pi over 2 minus alpha minus beta. And then, and this is a very, very important step, I'll use the associative property here to think about my first angle as being alpha, pi over 2 minus alpha, and my second angle as being beta. So what I'm going to do from here is I'm going to use the cosine difference identity to finish this problem. The cosine difference identity tells me how to handle the difference of any two angles. The two angles that we're thinking about here are pi over 2 minus alpha, that's the first, and beta is the second. So I'll just follow the prescription outlined above, and I will get cosine of the first angle, pi over 2 minus alpha, times cosine of the second angle, plus sine of the first angle times sine of the second. And that's great. And what I can do now is I can use these cofunction identities again, because I see right here a cosine of pi over 2 minus alpha, and I know that that is the same as sine of alpha, cosine of beta. And then I see right over here a sine of pi over 2 minus alpha, and I know that that is the same as cosine of alpha, sine of beta. Okay, so what I did was I came up with a nice new way to write sine's sum. Sine of alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta. And that identity is known as sine's sum formula. Sine's sum formula. From sine's sum, I could quickly work out sine's difference. I'll use the exact same idea from the last video. The last video said if you want to move from a plus sign to a minus sign or vice versa, you can simply think about negative angles, or the opposite of the angle you started with. So I can rewrite alpha minus beta as alpha plus negative beta. Those two are clearly equivalent. So I've rewritten it as a sum, and now I'm thinking about my first angle as being alpha and my second angle as being minus beta, and I'm following the prescription outlined here for sine sum identity. And I'll get sine of the first angle alpha multiplied by cosine of the second angle, which is minus beta, plus cosine of the first angle times sine of the second angle, which is minus beta. Once again, I'll have to use my even and odd properties. I remember that cosine is even, so I'll get cosine of beta here because cosine is even. And I've kind of learned my lesson this time. Here I see sine of minus beta, and I remember that sine is odd, so I'll pull out that minus sign and I'll write it as cosine alpha sine beta. That's great. Cool, so to put that together, this is sine's difference identity. I have sine of alpha minus beta is equal to sine alpha cos beta minus cos alpha sine beta. And you'll notice that there are some little differences between sine and cosine's sum and differences. This is sine's difference. Sine's difference identity. This time for sine, unlike for cosine, sine's sum has a sum and sine's difference has a difference. And sine also has this mix and match flavor where the cosine doesn't. Cosine pairs the cosines with the cosines. That's helpful as you start to remember them a little bit, kind of keep track of which one's which. All right, so I'll finish up this video here with deriving some formulas for tangent, which aren't so hard to do from where we have landed. And let's see how that's done. So for tangent, what about tangent? What about tangent? Does it have a sum and a difference formula? Okay, so which one I want to get first? It doesn't really matter too much here. Let's say I want to work out tangent of alpha plus beta. So naturally, one would say, okay, I know tangent, it's sine over cosine. That certainly hasn't changed. So I can rewrite it as sine of alpha plus beta over cosine of alpha plus beta. And I guess I could stop there, but you can certainly do better. In the numerator, you can write out sine sum, which is sine alpha, cos beta, plus cos alpha, sine beta. And in the denominator, you can write out cosine's sum, which is cos alpha, cos beta, minus sine alpha, sine beta. And once again, you could certainly stop there, but it makes some sense to see, is it possible to get this all in terms of tangents? After all, it's tan sum formula, so it seems weird to use sines and cosines. And you actually can. You can get this all in terms of tangents, and that's a nice way to know the formula, is all in terms of tangents. In order to do that, there's a little trick involved, and that involves multiplying by a well-chosen one. And I don't know that it's immediately obvious which one to choose to create some tangents out of this mess here. But you need something that's going to cancel out some cosine betas or sine of alphas. And if you stare at it long enough, and you're welcome to pause the video and stare away, play around a little bit, try some different things, you might see that this choice right here, secant alpha, secant beta, is the perfect choice for the well-chosen one. Just mark that right here. Of course, multiplying by 1 doesn't change our expression. So let's see why that works so well. I'm just going to think about multiplying it term by term here. When I multiply secant alpha, secant beta by that first term, the secant beta cancels with the cosine beta. And the secant alpha acts, of course, as 1 over cosine alpha to pair with the sine of alpha to make a tan of alpha. When I move to the second term, cosine alpha, cosine beta, and think about multiplying that by our well-chosen one, now the cosine alpha cancels with the secant alpha, and the sine of beta pairs with the secant of beta, leaving a tan of beta. And in the denominator, when I multiply my well-chosen one by this term here, let's try that again, well, secant times cosine is just 1. So secant alpha times cosine alpha and secant beta times cosine beta is just going to give me a 1 in that bottom left corner of the fraction. Minus, and the last term, sine alpha, sine beta. Of course, each of those sines are going to pair with the 1 over cosines to make a tangent, and here you would end up with a tan alpha times tan beta. And that right there is, just to bring down the left-hand side, Tan's sum formula. Tan sum formula is useful to know. Tan sum formula, for one thing, can be used to very, very quickly work out tangents difference. So I think you're catching on to this little trick by now. If you're trying to move from a sum to a difference and you're trying to see how things change, it really just comes down to even and odd properties. So I'm going to think about, instead of alpha minus beta, I'll think about this as alpha plus a negative beta. So my second angle, I'm thinking of it as being a negative, and then I'll pull out that minus sign if I'm dealing with an odd function. And a tangent, of course, is an odd function. So what that means is my numerator would change to tan alpha minus tan beta instead of a sum. And then in the denominator, I would get tan alpha tan beta as a positive, because the minus sign on the tan beta will come out and change that sign. And that will give me tan sum and tan's difference all at once. So tan sum and its difference identity. Okay, so next, in the next video, we're going to talk about how we can use these to get the so-called double angle identities. So I invite you to think about this for a few seconds. Is there a way you can take what you've just learned today and come up with a new way to write cosine of 2 theta, sine of 2 theta, and tangent of 2 theta? Because we know, of course, that these are not equal to 2 cosine theta, but there might be a better way. So that's what we want to come up with here. Is there a better way to rewrite these double angles? All right, see you in the next video.